Okay guys, welcome to part 2 of the video series dedicated to the understanding and intuition around friction. In part 1 we unpacked what friction is, where it comes from, and what the specific formulas are that give us a good understanding of the magnitude of friction. In this video we look at an applied example that's basically happening in one dimension, something just moving to the left or to the right. So if I have this block resting on a surface, say for example this was a wooden block on some grass, and I was asked to move it, I'm going to apply a pushing or pulling force to the right. The moment that this thing starts moving, there's going to be a frictional force that's going to oppose this motion. Note also that there are vertical forces acting on this object. The object has mass, therefore it's going to experience a weight force, and from Newton's third law there's an equal and opposite reaction. This object doesn't just move down, the grass exerts an equal and opposite force in the upwards direction. That's called the normal force. Alright, so I'm going to unpack all the vertical and all the horizontal forces separately. I'll start off with the vertical forces. The sum of all vertical forces, because there's no net acceleration vertically, means that the sum of all vertical forces equals 0. Alright, remember I have to put a convention in terms of my coordinate system, so anything moving up and to the right is given positive, anything down and to the left is given negative. That then means that the normal force is positive, the weight force is negative, and that equals 0. So normal force minus weight force is equal to 0. I take the weight force over to the other side. Normal force is therefore equal to the weight force. Okay, so that should be fairly obvious. Remember that weight is equal to mass times gravity, and since the normal force is equal to W, that means the normal force is also equal to mass times gravity, meaning that this object doesn't just go up and it doesn't go down, it stays flat. In terms of horizontal forces in the x direction, since I am creating movement, there's going to be a net acceleration to the right. Okay, that means that the net forces excuse me, I'm sorry. The net forces horizontally are going to cause mass and acceleration to the right. Okay, so I'm going to unpack the net forces acting on this particular object. What we have here is the force of the push or the pull minus the force of friction is equal to mass times acceleration. Okay, so I'm just going to kind of unpack this force of friction for a second. Remember in the previous video we stated that the force of friction is equal to the coefficient of friction. Coefficient of friction is a derived number, and it's basically how much friction this block will experience when it slides on this grass. So it's dependent on the surface texture, the surface roughness or smoothness, any lubrication that might be present, etc., 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 multiplied by the normal force. But we already know that the normal force is equal to the weight force, which is equal to mg. So that means the force of friction is equal to mu sub k mg. Same thing. Okay, so I'm going to plug this in for this force of friction over here. So now I'm sitting with the force with which I'm required to push or pull this object to get it moving at some acceleration, minus the force of friction, which is mu, sorry, let me just get this color right, mu sub k mg is equal to max. Alright, so since I'm trying to isolate how much force it is that is required of me, I'm going to take this over to the other side, and then we'll try and make sense of what it is that we're seeing. So the force of the push or pull is equal to mass times acceleration in the x direction, and then this becomes a plus mu sub k mg. Okay, so let's just try and unpack this for a second just to make sense of it. Remember, Newton's second law states that force states the following: force is equal to mass times acceleration. So in other words, if there was no friction here whatsoever, if I apply a force to this block with a specific mass, it's going to experience some acceleration. The acceleration that this object experiences is going to be proportional to this force. So if I double the force, I will double the acceleration. But it's also inversely proportional to the mass. So the heavier this is, the harder it is to accelerate. Okay. So that's in essence what we're seeing here in this first portion. Force is equal to mass times acceleration. However, if I factor in the force of friction, that means the force that I have to apply has to be greater than when there's no friction present. That's what we're seeing over here. If I account for friction, how much force I have to exert is going to be bigger than when no friction is present. That kind of seems intuitively to make sense. But let's just try and prove it. In one case, where I say no friction, I want to determine how much force is required of me in order to get that object to accelerate, and in the other case I do account for friction and how much more force do I have to then generate in order to get this block to move. So a couple of things I need to know. The mass of the object is 40 kilograms. The acceleration which it tends to experience to the right is 2 meters per second squared. It's saying that it's going to move at 2 meters per second every second that it moves. The coefficient of kinetic friction is 0.2. Okay, first case, no friction present, so it's just force is equal to mass times acceleration, which is 40 times 2, and that's going to give me 80 newtons. In the second case, it's basically this formula that I have up here. The force that is required of me is equal to this mass times acceleration plus this coefficient of kinetic friction, mass times gravity. So if I plug in the numbers, it's 40 times 2 plus 0.2 times 40 times 9.81. Okay, so if I kind of add all of this together, I get a rather large number, which is equal to 158.48 newtons. So it's almost double the amount of force that I had to apply early on. This is almost like 160. So the force of friction makes a significant contribution in this case, in terms of how much force I have to apply. So hopefully that's kind of settled that argument that the force of friction is a significant contributor and I can't just ignore it. Okay, in the next video, part 3, what I want to look at is if I had to start angling this force either up or down, what difference is that going to make in terms of how much force I have to apply to get this object moving? Is it going to make it easier? Is it going to make it harder? Is it going to make no difference at all? Okay, see you guys in part 3.